Welcome back, or welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Comet. A comet is an icy, small solar system body that warms and begins to release gases when passing close to the sun, a process called outgassing. This produces an extended gravitationally unbound atmosphere or coma surrounding the nucleus, and sometimes a tail of gas and dust gas blown out from the coma. These phenomena are due to the effects of solar radiation and the outstreaming of solar wind plasma, acting upon the nucleus of the comet. Comet nuclei range from a few hundred meters to tens of kilometers across, and are composed of loose collections of ice, dust, and small rocky particles. The coma may be up to 15 times Earth's diameter, while the tail may stretch beyond 1 astronomical unit. If sufficiently close and bright, a comet may be seen from Earth without the aid of a telescope, and can subtend an arc of up to 30 degrees, 60 moons, across the sky. Comets have been observed and recorded since ancient times by many cultures and religions. Comets usually have highly eccentric elliptical orbits, and they have a wide range of orbital periods, ranging from several years to potentially several millions of years. Short period comets originate in the Kuiper belt or its associated scattered disk, which lie beyond the orbit of Neptune. Long-period comets are thought to originate in the Oort cloud, a spherical cloud of icy bodies extending from outside the Kuiper belt to halfway to the nearest star. Long-period comets are set in motion towards the sun by gravitational perturbations from passing stars in the galactic tide. Hyperbolic comets may pass once through the inner solar system before being flung to interstellar space. The appearance of a comet is called an apparition. Extinct comets that have passed close to the sun many times have lost nearly all of their volatile ices and dust and may come to resemble small asteroids. Asteroids are thought to have a different origin from comets, having formed inside the orbit of Jupiter rather than in the outer solar system. However, this discovery of main belt comets and active Centaur minor planets has blurred the distinction between asteroids and comets. In the early 21st century, the discovery of some minor bodies with long-period comet orbits, but characteristics of inner solar system asteroids, were called max comets. They are still classified as comets, such as C 2014, S3, Pan-STARRS. 27 Manx comets were found from 2013 to 2017. As of November 2021, there are 4,584 known comets. However, this represents a very small fraction of the total potential comet population, as the reservoir of comet-like bodies in the outer solar system in the Oort cloud is about 1 trillion. Roughly one comet per year is visible to the naked eye, though many of those are faint and unspectacular. Particularly bright examples are called great comets. Comets have been visited by uncrewed probes, such as NASA's Deep Impact, which blasted a crater on Comet Tempel 1 to study its interior, and the European Space Agency's Rosetta, which became the first to land a robotic spacecraft on a comet. The word comet derives from the Old English cometa, from the Latin cometa or cometes. That, in turn, is a romanization of the Greek kometes, wearing long hair, and the Oxford English Dictionary notes that the term austere kometes already meant long-haired star, comet in Greek. Kometes was derived from komon, to wear the hair long, which was itself derived from kome, the hair of the head, and was used to mean the tail of a comet. The astronomical symbol for comets, represented in Unicode, is U plus 2604 comet, consisting of a small disk with 3 hair-like extensions. The solid core structure of a comet is known as the nucleus. Cometary nuclei are composed of an amalgamation of rock, dust, water ice, and frozen carbon dioxide, carbon monoxide, methane, and ammonia. As such, they are popularly described as dirty snowballs, after Fred Whipple's model. Comets with a higher dust content have been called icy dirtballs. The term icy dirtballs arose after observation of Comet 9P Tempel 1, collision with an impactor probe sent by NASA Deep Impact mission in July 2005. Research conducted in 2014 suggests that comets are like deep-fried ice cream, in that their surfaces are formed of dense crystalline ice mixed with organic compounds, while the interior ice is colder and less dense. The surface of the nucleus is generally dry, dusty, or rocky, suggesting that the ices are hidden beneath a surface crust several meters thick. The nuclei contains a variety of organic compounds, which may include methanol, hydrogen cyanide, formaldehyde, ethanol, ethane, and perhaps more complex molecules such as long-chain hydrocarbons and amino acids. In 2009, it was confirmed that the amino acid glycine had been found in the comet dust recovered by NASA's Stardust mission. In August 2011, a report based on NASA studies of meteorites found on Earth was published suggesting DNA and RNA components, adenine, guanine, and related organic molecules, may have been formed on asteroids and comets. The outer surfaces of cometary nuclei have a very low albedo, making them among the least reflective objects found in the solar system. The Giotto space probe found that the nucleus of Halley's comet, 1P Halley, reflects about 4% of the light that falls on it. And Deep Space One discovered that Comet Borrelli's surface reflects less than 3%. By comparison, asphalt reflects 7%. The dark surface material of the nucleus may consist of complex organic compounds. Solar heating drives off lighter volatile compounds, leaving behind larger organic compounds that tend to be very dark, like tar or crude oil. The low reflectivity of cometary surfaces causes them to absorb the heat that drives their outgassing processes. Comet nuclei with radii of up to 30 kilometers have been observed, but ascertaining their exact size is difficult. The nucleus of 322P SOHO is probably only 100 to 200 meters in diameter. A lack of smaller comets being detected despite the increased sensitivity of instruments has led some to suggest that there is a real lack of comets smaller than 100 meters across. Known comets have been estimated to have an average density of zero point 0.6 grams per centimeter cubed. Because of their low mass, comet nuclei do not become spherical under their own gravity and therefore have irregular shapes. Roughly 6% of the near Earth asteroids are thought to be the extinct nuclei of comets that no longer experience outgassing, including 14827 Hypnos and 3552 Don Quixote. Results from the Rosetta and Philae spacecraft show that the nucleus of 67P Churyumov-Gerasimenko has no magnetic field, which suggests that magnetism may not have played a role in the early formation of planetesimals. Further, the ALICE spectrograph on Rosetta determined that electrons produced from photoionization of water molecules by solar radiation, and not photons from the sun, as thought earlier, are responsible for the degradation of water and carbon dioxide molecules released from the comet nucleus into its coma. Instruments on the Philae lander found at least 16 organic compounds at the comet's surface, 4 of which have been detected for the first time on a comet. The stream of dust and gas thus released form a huge and extremely thin atmosphere around the comet called the coma. The force exerted on the coma by the sun's radiation pressure and solar wind caused an enormous tail to form pointing away from the sun. The coma is generally made of water and dust, with water making up to 90% of the volatiles that outflow from the nucleus when the comet is within 3 to 4 astronomical units of the sun. The H2O parent molecule is destroyed primarily through photodissociation and to a much smaller extent photoionization, with the solar wind playing a minor role in the destruction of water compared to photochemistry. Larger dust particles are left along the comet's orbital path, whereas smaller particles are pushed away from the sun into the comet's tail by light pressure. Although the solid nucleus of comets is generally less than 60 kilometers across, the coma may be thousands or millions of kilometers across, sometimes becoming larger than the sun. For example, about a month after an outburst in October 2007, Comet 17P Holmes briefly had a tenuous dust atmosphere larger than the sun. The Great Comet of 1811 had a coma roughly the diameter of the sun. Even though the coma can become quite large, its size can decrease about the time it crosses the orbit of Mars, around 1.5 astronomical units from the sun. At this distance, the solar wind becomes strong enough to blow the gas and dust away from the coma, and in doing so, enlarging the tail. Ion tails have been observed to extend 1 astronomical unit or more. Both the coma and tail are illuminated by the sun and may become visible when a comet passes through the inner solar system. The dust reflects sunlight directly while the gases glow from ionization. Most comets are too faint to be visible without the aid of a telescope, but a few each decade become bright enough to be visible to the naked eye. Occasionally, a comet may experience a huge and sudden outburst of gas and dust, during which the size of the coma greatly increases for a period of time. This happened in 2007 to Comet Holmes. In 1996, comets were found to emit X rays. This greatly surprised astronomers because X ray emission is usually associated with very high temperature bodies. The X rays are generated by the interaction between comets and the solar wind. When highly charged solar wind ions fly through a cometary atmosphere, they collide with cometary atoms and molecules, stealing one or more electrons from the atom in a process called charge exchange. This exchange or transfer of an electron to the solar wind ion is followed by its de-excitation into the ground state of the ion by the emission of X rays and far ultraviolet photons. Boshoks form as a result of the interaction between the solar wind and the cometary ionosphere, which is created by the ionization of gases in the coma. As the comet approaches the sun, increasing outgassing rates cause the coma to expand, and the sunlight ionizes gases in the coma. When the solar wind passes through this ion coma, the Bosch-shock appears. The first observations were made in the 1980s and 1990s, as several spacecraft flew by comets 21P Giacobini-Zinner, 1P Halley, and 26P Griggs-Scalerup. It was then found that the bow shocks at comets are wider and more gradual than the sharp planetary bow shocks seen at, for example, Earth. These observations were all made near perihelion, when the bow shocks already were fully developed. The Rosetta spacecraft observed the bow shock at comet 67P Churyumov-Gerasimenko at an early stage of bow shock development, when the outgassing increased during the comet's journey toward the sun. This young bow shock was called the infant bow shock. The infant bow shock is asymmetric and relative to the distance to the nucleus, wider than fully developed bow shocks. In the outer solar system, comets remain frozen and inactive, and are extremely difficult or impossible to detect from Earth due to their small size. Statistical detections of inactive comet nuclei in the Kuiper Belt have been reported from observations by the Hubble Space Telescope, but these detections have been questioned. As a comet approaches the inner solar system, solar radiation causes the volatile materials within the comet to vaporize and stream out of the nucleus, carrying dust away with them. The streams of dust and gas each form their own distinct tail, pointing in slightly different directions. The tail of dust is left behind in the comet's orbit in such a manner that it often forms a curved tail called the Type II or dust tail. At the same time, the ion or Type I tail made of gases always points directly away from the sun, because this gas is more strongly affected by the solar wind than is dust, following magnetic field lines rather than an orbital trajectory. On occasions, such as when Earth passes through a comet's orbital plane, the anti-tail, pointing in the opposite direction to the ion and dust tails, may be seen. The observation of anti-tails contributed significantly to the discovery of solar wind. The ion tail is formed as a result of the ionization by solar ultraviolet radiation of particles in the coma. Once the particles have been ionized, they attain a net positive electrical charge, which in turn gives rise to an induced magnetosphere around the comet. The comet and its induced magnetic field form an obstacle to outward flowing solar wind particles. Because the relative orbital speed of the comet and the solar wind is supersonic, a bow shock is formed upstream of the comet in flow direction of the solar wind. In this bow shock, large concentrations of cometary ions, called pickup ions, congregate and act to load the solar magnetic field with plasma, such that the field lines drape around the comet, forming the ion tail. If the ion tail loading is sufficient, the magnetic field lines are squeezed together to the point where, at some distance along the ion tail, magnetic reconnection occurs. This leads to a tail disconnection event. This has been observed on a number of occasions, one notable event being recorded on the 20th of April 2007, when the ion tail of Encke's comet was completely severed while the comet passed through a coronal mass ejection. This event was observed by the Stereo Space Probe. In 2013, ESA scientists reported that the ionosphere of the planet Venus streams outwards in a manner similar to the ion tail seen streaming from a comet under similar conditions. Uneven heating can cause newly generated gases to break out of a weak spot on the surface of comets' nucleus like a geyser. These streams of gas and dust can cause the nucleus to spin and even split apart. In 2010, it was revealed dry ice, frozen carbon dioxide, can power jets of material flowing out of a comet nucleus. Infrared imaging of Hartley 2 shows such jets exiting and carrying with it dust grains into the coma. Most comets are small solar system bodies with elongated elliptical orbits that take them close to the Sun for a part of their orbit, and then out into the further reaches of the solar system for the remainder. Comets are often classified according to the length of their orbital periods. The longer the period, the more elongated the ellipse. Periodic comets, or short period comets, are generally defined as those having orbital periods of less than 200 years. They usually orbit more or less in the elliptic plane in the same direction as the planets. Their orbits typically take them out of the region of the outer planets, Jupiter and beyond, at aphelion. For example, the aphelion of Halley's Comet is a little beyond the orbit of Neptune. Comets whose aphelia are near a major planet's orbit are called its family. Such families are thought to arise from the planet capturing formerly long-period comets into shorter orbits. At the shorter orbital period extreme, Encke's comet has an orbit that does not reach the orbit of Jupiter and is known as an Encke-type comet. Short-period comets with orbital periods less than 20 years and low inclinations, up to 30 degrees, to the ecliptic are called traditional Jupiter family comets, JFCs. Those like Halley, with orbital periods of between 20 and 200 years, and inclinations extending from 0 to more than 90 degrees, are called Halley-type comets, HTCs. As of 2023, 70 Encke-type comets, 100 HTCs, and 755 JFCs have been reported. Recently discovered main belt comets form a distinct class, orbiting in more circular orbits within the asteroid belt. Because their elliptical orbits frequently take them close to the giant planets, Comets are subject to further gravitational perturbations. Short period comets have a tendency for their aphelia to coincide with a giant planet's semi major axis, with the JFCs being the largest group. It is clear that comets coming in from the Oort cloud often have their orbits strongly influenced by the gravity of giant planets as a result of a close encounter. Jupiter is the source of the greatest perturbations, being more than twice as massive as all the other planets combined. These perturbations can deflect long period comets into shorter orbital periods. Based on their orbital characteristics, short period comets are thought to originate from the Centaurs and the Kuiper Belt scattered disk, a disk of objects in the trans-Neptunian region, whereas the source of long period comets is thought to be the far more distant spherical Oort cloud, after the Dutch astronomer Jan Hendrik Oort, who hypothesized its existence. Vast swarms of comet-like bodies are thought to orbit the Sun in these distant regions in roughly circular orbits. Occasionally, the gravitational influence of the outer planets, in the case of the Kuiper Belt objects, or nearby stars, in the case of the Oort cloud objects, may throw one of these bodies into an elliptical orbit that takes it inwards toward the Sun to form a visible comet. Unlike the return of periodic comets whose orbits have been established by previous observations, the appearance of new comets by this mechanism is unpredictable. When flung into the orbit of the Sun and being continuously dragged towards it, tons of matter are stripped from the comets, which greatly influence their lifetime. The more stripped, the shorter they live, and vice versa. Long period comets have highly eccentric orbits and periods ranging from 200 years to thousands or even millions of years. An eccentricity greater than 1 when near perihelion does not necessarily mean that a comet will leave the solar system. For example, Comet McNaught had a heliocentric osculating eccentricity of 1.000019 near its perihelion passage epoch in January 2007, but is bound to the Sun with roughly a 92,600-year orbit because the eccentricity drops below 1 as it moves farther from the Sun. The future orbit of a long-period comet is properly obtained when the osculating orbit is computed at an epoch after leaving the planetary region, and is calculated with respect to the center of mass of the solar system. By definition, long-period comets remain gravitationally bound to the Sun. Those comets that are rejected from the solar system due to close passes by major planets are no longer properly considered as having periods. The orbits of long-period comets take them far beyond the outer planets at aphelia, and the plane of their orbits need not lie near the ecliptic. Long-period comets such as C1999F1 and C2017T2 pan-stars can have aphelion distances of nearly 70,000 astronomical units, with orbital periods estimated around 6 million years.